Welcome everyone to this talk about building petabyte scale Postgres clusters with a tool called Bagger. And we'll talk a little bit about what this is, what some of the design decisions and trade-offs are, and we'll use it to explore certain aspects also of distributed data problems with Postgres. Some of you here know me, some of you don't. I've been working with Postgres since 1999. I've worked as a developer, as a basically application developer, database administrator. I've contributed one bug fix to Postgres, contributed a couple other patches, which of course were rejected for various reasons, and basically just generally been involved in patch review and all kinds of stuff. But at a place where I used to work, we used to use Postgres the way many people use Hadoop. And one of the systems that we built there is relevant here. And it's something I'm trying to rebuild in the open source space. Love if anybody is involved in this, interested in this, to get involved, so forth. So basically, I'm Chris. I have about 25 years of experience with Postgres, which is less than some people in the room. So let's see. Yeah, that's me. In this talk, we're going to talk about a few things. We're going to talk about what we built and why we built it. We're going to talk about the design from the perspective of my former employer in terms of why it was built the way it was. Part of it being just simply we needed something fast and this is what we could build. We're going to be looking at what we're changing as we're building the new version in open source terms, and also the sort of trade-offs that come with any sort of work in distributed space. So this particular tool has certain very specific requirements, and those requirements result in certain design decisions, right? And we'll talk a lot about the trade-offs that go into building, massive clusters of this sort of size. Just a little bit more about the context there. At Adjust, we had 2 petabyte scale environments. This is about one of them. This is our massive log management system. I can contrast it a little bit near the end if I have some time with our customer-facing data warehouse. But this one was write heavy, and it was more focused on write scaling than read scaling. So life before Bagger, we used Elasticsearch. Anybody here, just as a show of hands, run into cases where Elasticsearch doesn't scale? Few, yeah. So basically the problem is that Elasticsearch has a relatively chatty protocol, and oftentimes when you feed it enough data fast enough, this can actually cause problems in terms of ingestion. Additionally, when I've talked with Elastic people, they don't know of anybody using Elastic for more than 1.5 petabytes of data. So Elastic actually has some scalability limitations. We ran into them. By the end, we called our Elasticsearch cluster a very expensive dev null because we could write to it, but we could never read to it from it. Basically, we had a bunch of problems. We would have garbage collection stop the world events, which I'm sure it's better now with newer garbage collectors, but those would actually pause the world for long enough that a node would fall out of the cluster, and we'd have rebalancing, which would cause the whole problem to start again. So velocity made this system unusable. At the time we were ingesting, we had maybe a petabyte of data, and that was 30 days worth of data. So I'm just guessing that's probably like what? I want to say 3 terabytes a day or something. And then basically at the end when I left, we had 10 petabytes of data. Well, no, it'd have to be. And that was only 14 days of retention, so we were up at like 60 terabytes a day. So we had some specific problems with Elasticsearch. I mentioned the noisy protocol before. Anytime Elasticsearch would find a new field in these JSON documents, it would try to figure out how to index them. It would coordinate what kind of index there were across the whole cluster. And this made a lot of things very slow. We actually ended up having to use very strict schemas with Elasticsearch. We couldn't basically go schemaless because this problem would kill us in terms of the velocity. A second problem is that if you restart a node, everything rebalances. And this makes it very, very difficult at scale and at high velocity to actually restart servers on a cluster. It also means that instead of having a nice high availability system where if any system dies, the cluster more or less continues, you end up with a low availability system where if any system dies, things can go into a death spiral. And so, I mentioned they'd stop the world events before. This is probably better, as I say, with newer garbage collectors, but in our case, we were having, I think, 5-minute long stop the world events. Another problem that we had with Elasticsearch was actually quite interesting. If you fired a query that used up too much memory, you get a Java heap exception. And the client, being very helpful, would try the query again. The only problem is that that Java heap exception had just killed one node. And then, yeah, you get what's exactly going to happen, right? That's another great way to just kill your cluster, right? So at very high scales, Elasticsearch had some really pathological cases that bite us. Almost any system will have really pathological cases when you start pushing its scale to the limits because you're getting out of where it was designed for, and you're pushing it in ways that things will just go off the rails. So we evaluated a bunch of technologies. We actually settled on Postgres for the storage. And so we built Bagger. Bagger is named after those giant bucket wheel excavators they use for coal mining, with the idea that they're some of the largest land vehicles on Earth, and we were going to build some of the largest database clusters using Postgres, so we thought the name was appropriate. So Bagger was built with the idea that we need something now, we need to build something fast. So minimalist design. And as a result, we were able to get away from all these schema restrictions we had in Elasticsearch, simply because JSONB, Postgres doesn't care, right? We don't have to index everything in there. We can index what we want, and there's no communication between the nodes about what kinds of indexes we need to have. So very, very minimalist design. And one of the interesting things about it is because it's minimalist, it had linear write scalability to a point where we weren't able to find where there were any limits. I suspect the limit would have been the messages we could throw through the Kafka cluster. But if we ran out of that, I suppose we could set up another Kafka cluster, right? So not the end of the world. It would have required a little bit of extending to support a second Kafka cluster, but not too much. The biggest problem with this design, though, is that while we get linear write scalability, so if we double the number of nodes, we increase the write throughput by 2 times. We actually don't get much in terms of read throughput because every read query has to hit all nodes, right? So you're limited basically on what your slowest node can do. You trade off linear write scalability for basically no read scalability at all, which was fine in our use case because it's just a massive log ingestion. Now this is one of the things to keep in mind when you're building large distributed database structures, because once you're into the space, you actually have to think through very carefully where you're scaling out, right? Are you scaling out reads? Are you scaling out writes? Or you're trying to scale out both, because all of those have different considerations and you need to think through those, right? If you're scaling out reads, then having locatability of a record is actually really, really helpful, because then you don't have to query everything, right? But if you're only scaling out writes, then you don't need that. And if you need to scale out both, then maybe scaling out the writes into something where you don't have locatability, and then having each of those nodes move it into something where there is can make a lot of sense. And that's actually what we did with our with our customer-facing data warehouse. So that's a basic bit about the design at the beginning. So the original design basically is you write all these documents to Kafka. Each JSON document is a Kafka message. And then you set up your Kafka topic with basically a large number of partitions, so that when you have a consumer group here, each consumer group will read from a roughly even portion of partitions. And then we'll basically write each message to two different nodes on two different Postgres databases, right? So that we have some redundancy, because there's no way we're going to back this thing up ever. Part of the problem with backing it up is that this is petabytes of data, and it only has a 30-day retention period. It would take us longer to restore it than we would intend to retain it anyway, right? So why would we back it up? Instead, we just want to have redundancy so that we have as much protection as we can against data loss. So, so then the second thing is, then this means that everything is effectively randomly sharded. People call this chaos sharding. Basically, a single node, you can't predict where a message is going to go. It goes into various Kafka partitions, and that determines where it goes on the cluster, right? So you have this multi-threaded, we call it Schaufel, which is German for shovel. It's just a multi-threaded data shovel that loads data out of Kafka and shoves it in Postgres, or it can shove it somewhere else. You can load it out of Redis, throw it in Postgres. You can load it out of Redis, throw it in Kafka. You can throw it in, whatever. It's nothing more than a multi-threaded data shell, right? Now, one of the interesting things here is that we didn't want to index every field of the JSON. So we indexed 48 fields. We had an index with 48 columns wide. Anybody know what happens when you try to do this with stock Postgres? Yeah, I see a few people laughing. There's this wonderful value, index max keys, that's set to 32. It doesn't work. So we actually had to patch that up. We bumped it up to 64 for our builds, and we compiled our own Postgres for this. So, and then basically everything just was JSON-B documents. And we had a C language trigger that would unwrap the JSON-B, figure out what table to put it in, and then just write it there. We didn't use declarative partitioning for a bunch of reasons. First, it was way too slow in the time frame we were talking about. It might be faster now. But the second issue is that I'm not actually sure if you can partition on an expression. And I haven't tried that.
Yeah, now.
You can? Okay, so the comment is that you can now. But even if we could, you now have the next problem where if you're partitioning on multiple expressions where you're pulling data out of the JSON-B, you're going to have multiple marshalling runs of the JSON-B to get those multiple expressions, I would expect. So we may still be stuck with the same approach we're doing now, which is parse it once, generate a table, and write in there with a trigger. So yeah, we had a C language trigger designed to be basically as fast as we could make it. Had some interesting bugs at first, but we figured it out and fixed those. During this time, we really wanted to open source it. I went on talks promising to open source it, but we never had time. And the other problem is that when you take an internal corporate project and you try to open source it, you run into all these little cases which were built around your particular business, not necessarily just your use case, but things like names of things that are indicative of what you're actually doing as a business rather than trying to make this more general. And taking the time to actually get all those things out was really big, and we just simply never found ourselves able to do that. So time went on. I kept trying to budget time to get it done. We made some progress on it, but it never got quite to where we needed it to be, and so we never open sourced it. So then eventually I left Adjust. I actually did so because I had basically found myself in a role that was way too high stress, and it had started to cause health problems. And so I left Adjust. A couple years later, I started to meet with other people who had previously also left Adjust. We didn't get in touch with anybody who was still working there because obviously don't have rights to the original. So we got a whole bunch of people together and we were like, okay, well, let's compare our notes and let's actually build something general for everybody else based on this exact design. So there are basically 5 of us. The design looks similar from the outside with some significant changes, but of course the code base is 100% different. Restarting the effort, basically, we have, I think, 5 of us who were previously from Adjust and a few others basically coming in, basically taking notes about what the previous system looked like, and then trying to build an existing open source system. Now again, if you look at the trade-off questions, this was a system built for massively scaling writes, not for massively scaling reads. If we were to massively scale reads, we'd have to rethink a lot of things, right? But that's a different topic. It's also, well, it's not a different topic, but it's a different sort of direction that things can move. And basically, we started using existing open source components, existing frameworks. And our initial approach was start with what you know and then build out to what you don't. The issue is, if you're gonna build a new project, how many of you have tried to engineer a new project from scratch and decided to make lots of changes in the process? A few of you. How many of you have ever completed one of those projects? A couple of you. Great, I'm impressed. The problem is that once you do this, if you just start reconsidering everything, you'll try to fix everything you could think of that was wrong, and you'll end up with a large set of problems you didn't expect, and you will end up swamped, right? And so we basically decided to build what we know and then refactor. So go with what we know, so same basic design, but some major changes to make it more general. The idea is to have as minimal changes as possible in order to make it generalized rather than specific. The reason for doing this is you're going to have things that you know that might be problems. You're also gonna have things that you don't know might be problems that are actually gonna come up and bite you, right? And if you don't have a really good solid foundation, right, that you can start with and reason about changes you're gonna make, then you're opening up an open universe of problems that in a large, highly scaled system, you're probably never ever gonna solve. So again, this is aimed at minimizing that area, that sort of problem space. And then the idea is that once we get to an actual usable system, that we start evaluating components. So like a lot of things that people are gonna look at in the first version, they're gonna look at and go, why would you do it that way? Why would you choose Perl 5 for all of your orchestration and cluster management code? Well, it's because that's what the other system used. And so we had decided we would reevaluate after we get everything done the first time, right? Yeah, sure. If it's gonna work, then at least we have something to compare it to, right? If we don't ever complete something, then we never have something to compare it to. So we had experience with a system of up to 10 petabytes. We figure we can build something that can handle that, so we're gonna do that, and then we'll reevaluate. So initial technology choices. People will say, again, why Perl? Again, because it's what the old system used. Moose, I don't remember if the old system used Moose or not. Probably not. But if you're gonna write Perl 5, you might as well use Moose. At least in non-critical, or at least in areas where you're not like reinitializing the code all the time. PGObject is a framework I wrote like, I wanna say 18 years ago, which is just something that allows me to declaratively map SQL function, user-defined functions into Perl object methods. So I can just simply say, this method deals with this function, and I don't actually have to write the code. It just does it for me. Because we are going to reevaluate languages, we're gonna put as much logic in the database as possible, because that makes it real easy to swap out languages. Of course, the trigger is still super performance sensitive, so that's going to go in C. Although it's not going to be at all the same because, you know, in making things more general, we have to make like the dimensions that you're partitioning by quite dynamic and things like that, and that adds some complexity there. If we're going to have Perl, then we want to do a web front end. We're going to use Perl Dancer, just because it's what I know. If I'm going to grab a Perl front end, that's what I'm going to, or the Perl web services, and that's what I'm going to use. And then the people Adam who will work on the front end will pick a framework when we're ready for that. That's less performance critical, so I'm less worried about that. And then we decided to pick up etcd for cluster state handling as a reference implementation, not necessarily as a requirement. So in order to deal with the whole cluster state side, what we had decided to do was to have a pluggable module, that an API effectively that we could just plug into the software that would, in this case, write to etcd, but we could also write one that would go to, we can also have one that could go to Zookeeper, could go to Console, could go to, I mean, we could even write one that would use logical replication in Postgres. And yeah, that would be quite possible, actually. The only problem with that is a large number of logical connections, which might not be so good. So, those were our initial technology choices. But then basically the idea was once we get the underlying structure kind of similar to the way it was, but obviously different in its own ways, then we'll start looking into pieces we will replace. But we also made some immediate changes, which we'll talk about in the next few slides. So, data flow. This is kind of where it becomes much more interesting, I think. So you have a service network, a bunch of servers that are generating logs. They write their logs to Kafka. Kafka, then basically you have these Schaufel programs. Schaufel is German for shovel. It's this multi-threaded data shovel. And basically it just scoops up data out of Kafka and starts writing it into pairs of Postgres nodes. And the topology that I came up with was, again, paired nodes would basically mean a circle, right? A logical circle. So it writes to 2 nodes at a time this way. This way, if you lose one node or one node is out for maintenance, you still have access to the full data set. You have to lose 2 paired nodes before, or you have to lose 2 nodes before you can even possibly lose data. Then, if you're actually going to query it, then we start on the other side with this front end. The front end would then basically send queries through a REST API to this query proxy. The query proxy then generates SQL and runs it against every node. And granted, my diagram here shows 5 nodes, but this could be 500, right? And then what the query proxy will then do is it will then take the results as they come back, and they'll stream it back using chunked encoding so that you don't actually have to build a whole result set before you send it back. And you can just basically stream the whole set. So that's the data flow. And the big difference between what we're doing here and what my former employer had done is they didn't really have a query proxy. What they had was a Perl script that you typed in command line stuff to search. That meant that if support people needed to query this data, which they often did, they had to SSH to a host and actually run this program with a command line that they usually built in an Excel spreadsheet in order to get their data. And then it would dump it into a file, and then you'd have data running around that you weren't ever sure where it was. For, say, GDPR purposes, there's some issues there. I think they've solved that now, but that's the way it was when I was there. And that wasn't a very good user experience, so we decided to stream this out over HTTP. Now, the control superstructure is sort of interesting also. So there are a couple components not really mentioned on this slide, and I'll have to kind of explain it. But basically, the idea is you start with this sort of infrastructure as code framework here. And the infrastructure as code framework then is able to automate setting up various pieces of your infrastructure. So it can set up a front end, it can set up a query proxy. It could set up a metadata system, but probably not so much on that. It can set up data nodes, set up Schaufels, all that sort of thing. The big thing, though, is that this is true until you actually want to, say, take a node down for maintenance or things like that. And then we go from basically infrastructure as code to infrastructure as data. Okay? At that point, and I don't really have a slide describing this, so I'm going to go through it in some detail here. Basically, these metadata servers then end up as the point of truth for the state of the entire cluster. So if you have you want to take a system down for maintenance, you just simply write to this server, you set the status of this in just a normal table. This node is going down for maintenance. Then what happens is you have an agent that listens to the logical replication stream, takes the data out, puts that data in etcd or wherever, and then that propagates out. You have something else which is listening to that change set on those nodes, and that node goes, okay, that agent says, okay, I need to take my node down for maintenance, and it goes ahead and does that. So it's kind of a push-pull. I mean, it's a pull-based model that basically pulls everything out of the metadata server. It can mean that if there's a problem with communication there, then you may have a problem actually changing state of your systems, but it's not intended to be like a highly critical system. If you have to, you can just like take it down and shut down the related shuffles. And you could do that manually, including with infrastructure as code. But the normal intended approach is just simply to do it in the metadata server and let the changes propagate out. So this is intended to be a control center. We called it LankWork because in a bagger system, of course, you have the sort of central gear system. And so we decided to just keep going with with mining machine terms. So this is basically this. Now this is out of date because I've been working on things while I'm here. Our general node control infrastructure, including infrastructure as code, is now complete. Okay, the C language trigger is now in progress. I've been working on that while I'm here. I'm about, I want to say, a third to half of the way through. So hopefully in coming weeks, we'll have the C trigger done. It's not a small job, unfortunately, because there's a lot of performance critical stuff going through there, including caching plans and all kinds of stuff like that. We have a Postgres config that is used to support some aspects of the query proxy. That is now under review. It's not merely in progress. The query proxy and front end have not been done. But if there's anybody who's interested in getting involved, who would like to see any of this work, we would love to see, of course, people getting involved. And then I'm going to talk a little bit about Beyond GA, and then I'm going to come back to the whole like trade-offs thing, and then after that I'll take questions. So beyond GA, there are a bunch of things we want to revisit. Again, as I say, we started with build what you know, and then breakout pieces. We are trying to decide what language to rewrite the proxy, the query proxy in. Do we want it to be? We probably don't want it to be in Perl long term, just because I don't think that's probably a good language for that particular component. But do we want to do it in C, Golang, Java? Probably not C, because writing a web service engine in C doesn't strike me as very pleasant, but I could be wrong. So we're evaluating. We will decide after we get to GA. Do we want to integrate CitusDB into this whole process? Would that give us some scalability dimensions that we haven't thought about, particularly if it would let us find ways of scaling reads better? We'll have to look into that. But we're not going to do it on the first iteration because, again, we don't know, right? And this is one of the basic things that you learn once you get into distributed data is saying, I don't know, is actually a really, really good thing, and you just say it a whole lot. The number of ways of we can possibly scale reads. How do we want to do that? Figure that out. But I don't expect that reads will ever scale as well as writes, just because it's likely to be more expensive. Since instead of writing twice, do we want to go with binary replication? We'll need to benchmark that out. Last time we tried it, we were easily able to overwrite, basically easily able to overload the ability of the recovery process to apply the write-ahead log. So we'll have to look into that, see if it still makes sense, if the limitations are still there, or if it makes sense to support that as an option or as the main approach. Another one I'd actually like to spend a lot of time looking at is benchmarking with different storage options. Does it make sense to go with 32K blocks? If we go with 32K blocks, that would presumably mean a lot less toasting, right? And so it might mean less expensive retrieval of the document since we're always retrieving the document, right? It would mean less indirection, fewer hits on toast and things like that. So that's another thing that we definitely need to look at. And there are many more actually on the GitHub page. We have a tag of research, and it's quite there. I think there are a whole bunch of them, a whole bunch of items there. So on to the trade-off piece, and then I'll start taking questions. The first one I think is always really important to recognize is that scalability involves trade-offs, right? Once you're trying to scale out, you have choices on what you can prioritize, right? In this design, normally most of us are familiar with how to scale reads, right? We can add more and more binary replicas, and we can just scale reads that way, right? This is an example of how we can just scale writes, right? So it's kind of the opposite. It's kind of the opposite dimension. But if we're trying to scale both at the same time, then we end up with all kinds of questions of how do we optimize one workflow versus another, and is locatability helpful? Is it not helpful? Do we need like 2 stages of ingestion to get things to a point where we have locatability? All these sorts of questions, once you're into the whole scale out structure, become all about trade-off, one trade-off versus another trade-off, right? Second thing is, as I said before, one of the healthiest things you can say when you're into the distributed data space is, I don't know. And so consequently, it is really, 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 really helpful to literally benchmark everything. Anytime you're thinking about making a change or trying a new concept or something, benchmark it, because there are very likely to be things that you haven't thought about that may come up and affect the outcome. Like one example of this is one of the reasons we went with Postgres. When we had previously benchmarked things, we also looked at Cassandra. And Postgres had much lower disk I/O for the same scale of writes than Cassandra, right? So here's a case where benchmarking everything makes a lot of sense. That way you can figure out what works best for your scenario and choose appropriately. The last point I want to make is about specialization versus generalization. If you look at it, we're starting to see more and more sort of generalized scale-out solutions for Postgres, including, for example, Citus, right? Generalized solutions make trade-offs that work for certain general use cases. Typically, if you want something that is going to be extreme on a different side, though, then you may find that a specialized tool for that use case may perform much better. Like, for example, ingesting this much in the way of logs into something like this is going to be much easier than it is to try to use a general scaling out solution, simply because you're going to have overhead with making sure you have locatability and all these other sorts of considerations that you're going to have. So this is one of the other things that I would strongly recommend is think through, is a generalized solution good enough, or do I need specialization? Because if I need specialization, I'm probably going to have to do all the work myself, and it's going to look very, very, very different from the generalized solutions. A few bonus learnings here. Number one, before you start, know your requirements, right? It's very, very easy to get in the distributed space into an environment where you have built something which is great, but it doesn't match the requirements that you actually have, right? That's a really important topic here, right? If we wanted like something that was read heavy, this would not be an architecture that you'd use. Although you could use something like it as the first stage of an architecture, right? You could use it to bring in data, and then you could digest it and send it into something that's locatable, right? And actually that's how I would, if I were trying to build a data warehouse on top of it that was scaled out, what I would probably do. But if you don't need that, then why bother with, if you don't need the read scaling, why bother with the pieces that are related to it? The second point is that architecture is actually really important here, because architecture is going to define how the application scales out, right? And so picking an architecture that matches your use case is actually critically important. Now, when I say easy, I don't necessarily mean easy, but the point is that linear scaling of either reads or writes without any other considerations isn't actually all that hard, right? It's only when you have other considerations like referential integrity, for example, that you start to have some issues with write scaling, right? And read scaling itself isn't all that difficult. We really know how to do that. But when you're trying to do scaling on multiple, on both of these in multiple ways, and you're trying to make that scale linearly, that's actually suddenly much, much harder, right? And so when you're trying to combine them both, and you're trying to deal with all the rest of these, and you're trying to match, say, general use cases like foreign keys and whatnot, that's when things get much, much, much harder. And so at this point, I'm going to open this up for questions, and yeah. So anybody have any questions, thoughts, anything?
Can you expand a little bit more on your sharding strategy? Do you use any consistent hashing? If you added scale out the write, add a new node, does data redistribute, I'm just not very clear.
Okay, so you're asking about changes to the sharding topology, right?
Yeah.
So what we actually do is we do generational storage. So what we do is we generate a new topology when we change it. And then that old topology lives side by side until after the retention period's over. Oh. And then it can then we don't care about it anymore. So the idea is if we need to add more servers, we just add more servers, we create a new generation, and after the retention period, everybody's only on the new generation.
That's easier to
solve.
So
as I say, this was stupid simple. It was like the simplest way we could go about anything was done, and then we may think about some of these things later. Like we haven't ruled out the possibility of being able to do other kinds of resharding later. But the first approach is going to just simply be this generational topology.
And a follow-up question is on your read. I wasn't clear, did you just say that you just randomly distribute them to all your nodes? Which means that if I do a query, I have to search all the nodes, right?
That's correct.
So, if you get into the hundreds, right, the probability is high. One of the nodes, at a certain point in time, probability is high. One of the nodes may have a, gotcha issue, right?
Yes.
So mathematically, probably what happened, right? If 500 nodes, one of the nodes have a 10% chance of hitting, then your query will never be complete, or a high chance that your query will.
So the point is that because we write to multiple nodes, we have a backup basically of each node on another node, and so we can take a node out for maintenance while still making that piece of the data set available on the other component. Go ahead.
Yeah, so you're talking about you have the two or in versions of the data kind of distributed through your through the databases. Where do you do the deduplication of the values at the query proxy, where you basically like I'll get two instances of the data back, and then just you dedupe it there?
A great question. So the question is about the question of how we avoid querying the same the copy of the same data. What we are doing at present is basically the copy is in a separate schema, and so we can effectively independently query one bucket versus another bucket versus another bucket. And that avoids that problem, and then when we have to shut down a node, then we can query the other bucket too on the other node that has that bucket. So it's, of course, that also means that your read throughput is now reduced because you're having to put more reads through that one node. But yeah, that's the way we deal with that problem.
So if I understand correctly, write here means append data.
Yes.
So it's ingestion only.
It's ingestion only. It's read, retain, drop is the usual case. But if people wanted to keep it around forever, they just need more and more storage, and then we'd have to figure out a solution to that. But
so update goes to the application to read, modify, and append again.
So the primary use case of this is you have a fire hose of logs, and you need those logs to be available and trackable for auditing and things like that, or debugging. Like the case at Adjust included cases like support needs to know what queries we saw from customers so that we can tell them what we actually processed on their behalf. But it's not usually an analytical, nor is this data ever going to be updated in this particular system.
So all queries that go to Postgres are mainly like insert a blob and read a blob.
Yeah. They're either insert or they're either copy into it or they are read, select. Yeah. Now, if you need to be able to do updates, then you have to have some other ways of handling that. Like, there are ways of doing that, but you wouldn't do it in this specific system. Are there any other questions? Go ahead.
So since you're treating Postgres as append only, effectively, what kind of configuration optimizations did you do to those Postgres systems to enhance to optimize for append only, the append only scenario where you're not doing deletes, you're not doing updates, you're probably just dropping partitions instead, or for whatever it is you're doing for the drop portion.
So yeah, great question. There are a couple things. First of all, there are a couple of important points here. The first is also we're never ever doing index-only scans, right? So the first thing we do is we disable. Unless we are going to retain these tables for a long time, we will disable, or actually we should probably always disable auto vacuum on them. And if we're going to retain them for a long time, then we should probably manually vacuum them at one point just to simply freeze the rows, right? The second thing is that we need to think through storage carefully. If we are actually not going to read very much of this data, and we're really writing to it hard, then it makes sense actually to get better performance by going with ZFS. The reason for that is that you can trade CPU cycles for disk IOPS. And in this particular workload, you can actually get improved write performance. It's not usually the case for databases, but it is the case in this particular case. If you were going to be reading more of the data, you don't want to do that because now especially if you have decided to put this on spinning disk to pack in more data, your reads are going to get really, really painful because your sequential disk I/O is suddenly going to be random on the physical layout on the disk.
I was curious how important Kafka is in the front. Would it be feasible to write directly to the Postgres instances from the applications?
So the big thing is that, so the big challenge here is that you want to be able to batch your writes as much as possible. And the reason for this is that Postgres is much better at handling you're going to have much better throughput if you have a smaller number of streaming writes than if you have a large number of small individual writes, right? And so, so something like Kafka can be very important. If your application wants to do all that batching and you don't have very many instances, then sure, but the problem to that is then you probably wouldn't need, well, first of all, you wouldn't need to use Shuffle, but you're going to have all this problem of the application having to decide where to write it to. So I think Kafka is really helpful because it lets us do the distribution and it provides that, that ability to just kind of, simplify the management of the data coming in so that it's an actual fire hose rather than a whole bunch of massive number of sprinklers, right?
So you said you don't want to vacuum. Do you have issues with, so you're not getting bloat in the tables because it's just insert only. What about transaction ID wraparound since you're constantly ingesting?
Okay, so to kind of like sort of repeat what I said with a little different emphasis. If you're not going to be holding the data for very long, then vacuuming doesn't make any sense because you drop the partitions, right? And if the partition's gonna last, say, a month, which is gonna be typical especially if you deal with GDPR, then you're basically, if you're not hitting the transaction wraparound point in like a month, then you're dropping the tables in the meantime. It's not going to be a problem. If you're going to be retaining this data for a very long time, then what I said before is you want to probably you still want to disable auto vacuum because you don't want it to trigger generally, but then once you're out of a certain point, you may actually want to vacuum it in order to make sure that you can freeze the tuples, and then you actually might want to enable auto vacuum onto it so that if you somehow write to the table at some point that it will do it. Also, if you disable auto vacuum, it will still do transaction wraparound vacuums on the table. You just really don't want it to do them to all your tables at once. That would be a total disaster. So I think that's all the questions we really have time for. They have to get ready for the keynote. If people have other questions for me, feel free to talk to me in the hallway. So thanks so much.